Okay, ladies and gentlemen, here we go. Infinite sequences and series. We're got our second look here. Yesterday we talked about limits. We talked about the idea of infinite sequences, and we even talked about that a sum of an infinite sequence would really only make sense in the geometric case whenever the r value was some fraction less than 1, right? But still positive, right? So we're going to talk about that today. So what was our formula for S sub n? In a geometric, it was what? A sub 1 minus A sub 1 times r to the n all over 1 minus r, right? So that was our formula for S sub n. So if I wanted to say derive a formula for S sub infinity, this is weird looking. Actually, maybe I'll do this work in yellow as we derive it.
Why? Because your mind gets stressed over infinity and yellow's the color of stress.
Calms people, I don't know. So if I want infinitely many terms that I'm finding the sum of, I'm going to take the limit as n goes to infinity of that formula. Right? And now there's two cases for us to consider. Okay? The first case, bless you. If the absolute value of r is greater than 1, all right, then raising r to the n is going to get bigger and bigger and bigger and bigger and bigger, and this limit will not exist. All right, so limit does not exist, right? Case 2, what about if the absolute value of r is less than 1? Then what happens to the limit as n approaches infinity of specifically my r to the n value? What does that equal?
Get smaller and smaller and smaller.
It's going to get smaller and smaller and smaller and smaller and smaller.
Less than 0.
Well, absolute value took care of that. So that's going to equal 0, right? And if this is 0, then this whole term is 0, and a sub 1 minus 0, a sub 1 is not influenced by n, so a sub 1 is just approaching a sub 1. 1 is not influenced by n, so 1 is just approaching 1. R is not influenced by n in this denominator, so r is just approaching r. So when I calculate that limit, in this case too, I would end up with S sub infinity, the sum of an infinite list. How crazy is that? I love it. Right? Is going to be a sub 1 all over 1 minus r. How simple. How beautiful. What? Right? Because this whole term went to 0. Craziness. So, wow. Good times. So let's do an example of this, I guess. So we'll do a regular old example. So what if this is my list? What if I've got 1 and then a half and then a quarter and then ... forever? And let's say I want to find the sum of this infinite list. Let's label what we know. A sub 1 is 1. What about my r value? You could do a fourth divided by a half, or a half divided by 1. That sounds easier. So r is just a half. It's repeated multiplication by a half, right? So each term. What's n equal to? Infinity, right? That's what we're going to be doing. And I don't need any other values. And what is a sub n equal to? I don't know.
0.
Yeah, the limit is,
You don't need it.
it's approaching 0. We agree with that much. So, but we don't need it. Blah.
1 over infinity.
So, what we've got here, if I want to find S sub infinity, The sum of an infinite geometric series, guys. How crazy is this? How crazy is this? All right? It's going to be 1 over 1 minus a half. So what's that? 1 over 2 halves minus 1 half is 1 half. And then I can multiply the numerator by the reciprocal of the denominator. 2. It is not about 2. It is not rounded to 2. It is 2. The sum of infinitely many terms is 2 here, guys. What?
Almost 2.
Exactly 2.
No, because it would be infinitely close. It would be asymptotic.
No. If you stop the list after like your first 100 terms, it would be close to 2. If you stop the list after the first 1,000,000 terms, it would be close to 2. But if you actually keep going, if you added up all infinitely many of them, all of those little pieces end up perfectly filling in like the value of 2. Because we don't need them. And that even those questions are kind of obsolete. It doesn't make sense. 2 halves minus 1 half is 1 half, yeah. All right, so, and then if I wanted to find out, what if I started my list here, I could have just excluded that.
It'd be 1.
That's just 1. So a half plus a fourth plus an eighth plus a 16.
And if you started out a fourth, it'd be a half.
Yeah, so, I don't know, guys. Isn't that like a little bit mind-blowing?
That's exactly 2.
Right? Like, imagine, I guess, like, what if, like, Scrooge McDuck was, like, so obsessed with counting his money, and then, like, you know, like, there's the coin, like, a pieces of 8, where it's literally, like, a coin that was cut into 8 pieces. Like, what if he had money that was like this? He's like, 1 gold coin. Oh, this one's only a half of a gold coin, and then a quarter of a gold coin. He would spend forever counting his money
To 2 gold pieces.
to only find out that he has 2 gold coins. Wouldn't that be amusing? And then he just wasted all of his time. But maybe that's really what he loved. He just loves counting his money. He doesn't really care about how much he has as long as he can count it.
I don't know. I think he probably cares about the
Would he be happier with a finite amount of coins or an infinite amount of coins that only added up to 2?
money. Probably a finite. Because an infinite amount of coins added up to 2 would look like...
Now, if both of these were like, if both of these coins ended up being pennies, I guess like you barely have enough pennies to rub 2 pennies together in your pocket. Or you'd rub 1 penny with infinitely many fractions of other pennies.
Can people online hear you right now?
Yeah. Are you embarrassed for me, Cade? Is that what? Okay. But yeah, I don't know. I just think that's so crazy.
You know what else is funny?
What?
It sounds like you're having a conversation with yourself because they can't hear us.
They might partially, yeah. A little bit. Well, I added, well, since I realized I was using my headset, but it wasn't, I have to, every time I start it, reselect the headset as the main mic. So it is a little bit better in this video compared to some of the other ones you may have listened to. But yeah, it still is picking your voices up a little bit. But anyways, let's do another one. I don't know. Let's find a geometric sequence. What's a good one? What if I've got 12, and then let's say I've got 8, and then let's say I've got ... And let's say I told you this is geometric. So what is a sub 1? 12. R. I love it when I love sequences that have R values that you wouldn't necessarily think were fractions, but then end up being fractions. Because like the first couple terms, or 3 terms, or 4 terms, are integers. So let's see. So that's 2/3, right? So and look how great this formula is, guys. It's got 2 pieces to it. 2. How great is that?
It's got 2 variables.
Yeah. So 1. Nope.
12.
12 over 1
And
minus
you just write the 2 in.
2/3.
You had a 1 when you just write
Yeah. Well, but there's a difference between a 1 that was only ever meant to be in the ones digit compared to a 1 in the tens digit. Seriously. They're completely different classes of 1. That 1 didn't deserve to be in a 12. I had to erase it. So, anyways, so that's going to be 12 over, what's 1 minus 2/3?
1/3.
1/3. You could do some fraction work if you want.
36.
So 36. So the sum of this infinite list is 36. Cool stuff, huh?
No big deal.
Yeah. My mind is still blown, guys. We just added infinitely many numbers together, and we did it in what, 30 seconds? 40 seconds? I've got all day now. This is great. I'm not going to be wasting my weekend still adding this list up.
So next year you should do a thing where you give the class the beginning, like, until...
Yeah. That would be awesome. Like, as a side quest, add this list.
Whoever gets the farthest wins.
It would be awesome.
They get, like,
I love it.
50 gold pieces. But
All right.
Right before it's due, you just say do this, and
Like,
then
I win.
you win.
I win. I win. I'm the closest. That'd be terrible.
Terrible.
Let's see. How about this? What if I want to write as a fraction? Ready? Watch this one. What if I've got 0.3 repeating? Let's do that. Or I could make it interesting. Yeah, we'll start with this.
1/3.
Whoa, you're a genius. Or I could make it 0.32 repeating if we wanted. You want to have it interesting? Yeah, let's make it a little more interesting. So, in order to write this as a fraction, watch this interesting trick. I think I foreshadowed it the other day. So this is the same as 32 hundredths
Or 8/20.
plus 32 with 4 zeros plus 32 with 1 0 0 0 0 0 0 plus ...
Fractal.
Do you guys agree with that? Right, 32 hundredths, right? This is 0.32 plus 0.0032 plus 0.000032. And if I added up this list of infinitely many fractions, that would be the same as 0.32 repeating. Do you guys agree? Right? Now I want to point out this is not going to be 32 over 100, right? 32 over 100 would just be 0.32 stopped, right? I want infinitely many of them. So according to this list, what would A1 be? 32 over 100. What would R be?
1 over 100.
1 over 100, right? Because the numerators are all the same. It's just adding 2 zeros to the denominator. You could divide this by that in order to get that as well. All right? So 1 over 100. So let's plug it in our formula. Handy dandy. S sub infinity, the sum of this infinite list, is 32 over 100 over 1 minus 1 over 100. I'm going to work horizontally here just because I feel like it, because I'm also running out of room. So 32 over 100 over, let's see, that's 100 hundredths minus 1 over 100.
99 hundredths.
99 hundredths of root beer on the wall. Let's see, so here we go. And then that's 32 99ths.
Yep.
Because the hundos cancel out, right?
Yep.
Ching, ching. Or whichever way you end up simplifying that is fine. So 32 over 99 ends up equaling that. Let's see, how about now for my favorite. This is, do you guys get that? Yeah. All right. Does 32 99 simplify? 99 is divisible by 3 and 11 and more 3.
9.
No, and 32 is not divisible by 11 or 3, so.
Divisible by 2.
No.
It's divisible by a bunch of 2s.
Lots of 2s. 2 and more 2, yes.
2, 2, and more 2. Nothing but 2.
All right, here we go. Write as a fraction 0.9 repeating. This is like my favorite. This might be my favorite number.
Oh, this is...
And no spoilers. No spoilers. Let's see, could we write it as the sum of fractions?
Yes.
This would be what?
9 tenths plus 9 hundredths plus 9 thousandths plus
All right. So that is the same as that infinite sum. Agree? Disagree?
Yeah.
So a sub 1.
Oh, yeah, I know it.
R. What's R? 1/10. So let's plug it in the formula. And I will get the sum of infinitely many terms is 9/10 divided by 1 minus 1/10, which is 9/10 over 10/10 minus 1/10 is 9/10. Gentlemen in the back, right? 9/10. And what is 9/10 divided by 9/10?
1.
1. So apparently, as a fraction, 0.9 repeating is written as 1. You could write it as 1 over 1 if you want.
One of those weird.
And now we just proved it using the sum of an infinite list. How great is that?
Oh, that's up on your clock, too.
Yeah, and 6.9 repeating would be 7, right? Yes, indeed. So yeah, I've done a couple other proofs of this. I think I did some of them last year with you guys, maybe. But yeah, I mean, well, think about if 0.3 repeating is 1/3, right? 0.6 repeating is 2/3. By the way, 1/3 is the same as 3/9. 2/3 is the same as 6/9, and then 0.9 repeating would be 9/9.
3/3.
Or 3/3. Which is 1. It's not a paradox. It's just there's multiple ways of writing the number 1.
In theory, it should be like barely below.
No, it's exactly
barely
1.
Below a 1.
It's not rounded. It's equal. Isn't that great? I love it.
Yeah, I keep saying it. Maybe you'll fry my brain like that robot from Star Trek that was destroyed by a logical paradox.
Yes. Last problem. Write as a fraction. What if I have 2.13 repeating, where just the 3 is repeating?
Oh boy.
So, could you guys help me write this as a sum of some fractions?
2.13.
This would be 2 plus 1/10 plus
300 plus 3 4,000 plus 3 10,000.
Is this a geometric sequence?
Yes.
What's the pattern?
Take the shot.
What is a sub 1?
2.
No.
What do I multiply that by to get 1/10?
It isn't a geometric pattern. It's a couple of numbers plus the geometric pattern.
Perfect. How about this?
That's a geometric pattern.
Okay. So this will be 2.1 plus whatever I've got over there, right? So so what is a sub 1 in this list? 300ths. And what is r in this?
1/10.
1/10. Well, if I'm starting here, I'm only adding 1 0 to each of these. So that's why r is 1/10. Oh, sorry. What was that? No? Okay. All right. So this list, by the way, is the same as 0.03 repeating, is what this is representing. So it's just the 3 that's going forever, is what we got. So let's find the sum of that list. So S sub infinity is going to equal 300ths divided by 1 minus 1/10. Gentlemen, in the back. what is that denominator going to be? 9/10. Equals.
27.
It might be easier if I multiply by the reciprocal of the denominator. That looked like Planck's face right there, didn't it? Almost. Almost. I'd say almost.
390.
So 3 goes into 3 one. I just said one. Did I set that up right? Yeah, multiply by the reciprocal, right? Yeah.
130.
10 goes into 10 one. I keep saying one. Guys, help me. Ah!
It's 1/30.
1/30th? Is that?
Yeah, it's 130.
Plus
1
3 times 10 is
30th.
30. It's 0.03.
Mm.
2.1.
Yeah. Do you guys believe that 1/30th is 0.03 repeating?
Yeah.
Well, I suppose 1/3 would have been 0.3 repeating, right? And then having another 0 would just shift it over 1 decimal. Yeah, okay. So let's figure this out. So this is 2 plus 1/10 plus 1/30th. What am I going to have to do? Get some common denominators. Doing the math. Gentleman in the back. Calculating fractions.
Dora.
64/30ths, apparently.
Or,
yep, thank you. Classic. 15ths, 32/15ths. Let's see, do you guys believe that? Would you have thought that this looked like 32/15ths to you?
yeah. Looks like 30.
Let me see if my old calculator's up and running. No, don't lag out. Okay. Up, oop, up. Oop. That was a white screen emulator you saw there for a minute. It perfectly emulated a white screen. There's a whole lot of background programming that was required to do that. It's pretty good. So let's see. 32 divided by 1/5. Got a little bit of lag. Hit enter. 2.13. Looks like it's kind of repeating. So, well done, ladies and gentlemen. You are now able to add infinitely many things together, depending on what those infinitely many things are. Have a great day, everybody, in the internet land.